Okay, so you guys had a couple days to do the homework. So let's start with some answers. What's the answer to the first question? Two agents, values uniform 0, 1, uniform 0, 2. How would you show that the first price auction is not socially optimal in Bayes-Nash equilibrium? Yes?
So this is pretty rough, but for the 0 to 2 guy, he would never bid more than 1, so you would have some piecewise linear function mapping it, his value to, well, his bid from his value to somewhere between 0 and 1, and then you could maybe show that if they have, and then 0 to 1 would also have some a linear bid function, and then you could show that if the second player's utility was in some range, it might be higher, but because they had different bid functions, that the first player still might be lower, even though the second player had a higher utility.
So I think the best way to start answering this question is to start from revenue equivalence, from the payment identity. Suppose it was efficient, right? Then it would have to be revenue equivalent to the second price auction, right? Which would mean you should be able to calculate the payment rule and the strategies from using the second price auction and revenue equivalence, just like we did for two players uniform 0, 1, right? And so the idea to solve this problem is to start from that. Start from, if it's efficient, it's revenue equivalent to the second price auction, and then try to get a contradiction.
Okay.
And the contradiction you're going to get is you'll solve for the strategies, and you'll be like, huh, both players should be bidding their value over 2, essentially, as long as they're bidding at most 1/2. But then the higher player is not going to bid more than 1/2 if the lower player is stopping at 1/2. He's just going to put a point mass at 1/2, right? So that's what you would derive from using revenue equivalence in this scenario. A point mass at 1/2, and that's true because in the Vickery auction, the second price auction, right, the second player, if his value is above 1, he's not going to pay, he's going to pay an expectation 1/2. Right? The expected second highest value for any value as above 1 is it's uniform 0, 1 to the other guy, so it's 1/2 is what he's paying, so it's a point mass, right? And so they're both bidding their value over 2 up to 1/2 is the highest bid, and then the highest bidder is putting a point mass there. Is that an equilibrium? No, why not? Because if the second player is bidding a point mass at 1/2, the first player could bid epsilon more than that and win all the time, and would certainly want to do that instead of tying with this point mass, right? So point masses don't tend to happen in Bayes-Nash equilibrium for continuous distributions, and for good reason, because you always want to bid just above them. And so that would show that if you assumed, that would be the contradiction. It'd be, well, that can't have been an equilibrium. Good. So given auction with pay your bid if you win semantics, that is efficient. Okay, so what do I mean? I mean the auction gets bids, it chooses a winner somehow, and then the winner pays their bid. Okay, so the free variable here is, has to choose a winner. It's some function of these bids. Yeah.
So I guess you implement like the Meyerson optimal reserve price that we did yesterday, but here the glitch is they each have their own reserve price, which is it would be
socially optimal. This is welfare we're talking about, not revenue.
So then it is a Meyerson optimal, but it's probably in the same form, which is they each have a different threshold, which if they cross it, then they win. They need to both. No, that is wrong because if then they're both under and you give it to neither, that's inefficient.
Yeah?
Miles say it's very strange. I think if we constrain that the bit is, we only accept bit below 1/2, then it will be an equilibrium. Everyone will be, half of the valuation between 0 to 1 and 1 to 2. The higher bit will always be 1/2.
That's exactly right, actually. So what was the problem with the equilibrium? We were going for a counterexample in part A, right? We solved for equilibrium using revenue equivalence, but then player 2 was putting in a point mass at 1/2, and the problem was it wasn't equilibrium because player 1 could bid epsilon above that and then win. So let's just rule that out. Okay, how do we rule that out? The allocation rule is the highest bid wins unless you bid above 1/2, in which case I pretend you bid 1/2. That would be an efficient first price auction for 2 players, uniform 0-1. Okay, what's the virtual value function for uniform 0-2? Do you guys see the homework? That was the easiest question.
2v minus 2.
2v minus 2. Thank you. Okay, so what is the revenue optimal single item auction for 2 agents uniform 0-2? Yes. So that is what, in other words? The second price auction with reserve 1. Fantastic. And that's because 1 is the inverse virtual value of 0, 2v minus 2. Perfect. Okay, what about 2 agents with values uniform AB? What's that?
Same with reserve B minus A over 2.
Speak up.
Same with reserve, the different reserve in B minus A over 2.
The suggestion was the reserve was B minus A over 2.
B plus
A plus B over 2. Both those are incorrect. Let's think about just, suppose you just had 1 agent. Forget the 2 agents deal. Suppose you had 1 agent. Where's the chalk? Ah. Suppose you have 1 agent, uniform AB. And now let's pretend for a minute it's uniform 0B. What would be a good reserve price? B over 2, right? Well, if A is below B over 2, then we're already throwing out those bidders anyway. So what's the difference between uniform 0B and uniform B over 2B? Really, it's just scaled up distribution, right? So mathematically, the same thing should be happening, right? And if A is anything between 0 and B over 2, you just exclude all those bidders up to B over 2. Of course, if A is above B over 2, well, then you set a reserve price of A, right? So it's a second price auction with reserve the max, the max of B over 2 and A. Okay, two agents, uniform 0-1, uniform 0-2. So the virtual value functions we're talking about are these. And we know who wins, right? Who wins is the player with the highest positive virtual value. So we know that player 1 better bid at most 1/2, and player 2 better bid at most 1. Right? But then what?
Player 2 would never bid more than 1/2. Or like, equal to player 1 would never bid more than 1/2.
Well, we already know that player 2 has negative virtual value if they're bidding less than 1, so they have to bid more than 1.
Okay.
Right? Okay, so we know that B1 must be greater than or equal to 1/2. B2 must be greater than or equal to 1 for the player to win. And how do we decide which of the two wins if they're both above the reserve? Whichever one of these is bigger, which is? So player 1 wins if? If that's true, right? So what auction is this? It's kind of like a second price auction where player 1 has like a 1/2 benefit, right? They get a bonus of 1/2. So it's like biased in favor of player 1, the low valued player, right? You can draw, it's nice to draw the region of like where you win. So plotting player 1's value here and player 2's value here, right? Player 1 has to bid above 1/2 to win. Player 2 has to bid above 1 to win. And if they both beat their reserve, then we trade them off equally. That's a very bad picture. So player 2 wins in this region, and player 1 wins in this region. And that is 1/2. Right? It's a weird auction. It's not an auction that you see get run very often, right? All right, only one problem left. N agents, uniform 0, 1, and a public good. What does that mean? That means either I can serve, it's like I build a bridge, right? If I build a bridge, everyone can use it. If I don't build a bridge, no one can use it. And this is kind of weird for a public good, but let's suppose I'm trying to maximize my revenue building this bridge. Okay? What auction maximizes revenue? Yeah?
I think that the option that maximizes the sum of virtual value is the revenue option. The sum of all agent values greater than n over 2. Then I make this to the otherwise I would call.
Exactly right. So if the player's values sum to more than n over 2, then you build the bridge. Otherwise, you don't build the bridge. And what do you charge them? Well, you charge them the critical value for building the bridge or not. For if they can lower their value to what, then you don't build the bridge, right? Why was that? Well, we just took this equation for virtual value, we summed it over the n players, and we said, when is that sum bigger than 0? Right? And that's exactly when the sum of the values is bigger than n over 2. Okay, what's the expected revenue of the optimal auction? And I said use big O notation. What I mean is I don't care exactly what the constants are, but I want to know how it grows with n. Yeah?
My calculation isn't very rigorous, but I think that if you sum up n uniform valuation, it's close to a normal distribution with standard deviation of square root of n, which means that if you choose a unit length of the middle of that distribution, that will be about 1 over square root of n. Then you times n, which is every agent has the same expected payment. Then you get about square root of n, O square root of n revenue.
That's fantastic. right? So here's the way to think about this. What are the virtual values distributed like? Well, the value is uniform 0, 1. So virtual values, 2v minus 1, is uniform what? Hello? Uniform minus 1, 1, right? So I can think of taking n of these as like a random walk on a line where I'm equally likely to go forward in expectation 1/2 or backwards in expectation 1/2, right? And you know if you take a random walk on a line, if you studied random walks at all, that after n steps you end up at square root n from the origin. And you either end up at positive square root n or negative square root n, right? And if it's negative, you just throw it out. You don't build the bridge. So you get the expected positive amount, which is about square root n. Great analysis. Okay, so thanks for doing your homework. I'm now going to talk about approximation and mechanism design. Again, we're asking how a social planner should design the rules of a system so that good things happen when the agents play strategically. And we're going to do theory. And so what are the goals of a theory of mechanism design? We'd like it to be descriptive. We would like the mechanisms that we come up with in the theory that we solve for, if we look out in real life, we actually see them. So people actually use these mechanisms, so it describes behavior of all the practical mechanism designers out there. We like it to be prescriptive. If someone came to us and said, hey, I got to design a new mechanism for some problem, what should I do? You'd like to be able to give them some suggestions. If the CEO of some company says, hey, I've got to come up with a new auction for selling widgets on the internet, then you want to be able to say, I can help you solve that problem. You'd like it to be conclusive. You'd like to be able to pinpoint salient features of good mechanisms. So you can tell good features from bad features so that you can make these suggestions of, I think that's a good mechanism or I think that's a bad mechanism. And you'd like it to be tractable. You'd like that the mechanisms that come out of this theory to be ones that you could actually really implement in real life. Okay, so the informal thesis for this lecture is that approximate optimality is really good at doing all of these things. And it'll work hand in hand with the classical theory of optimal mechanisms to really extend that theory to cover many more settings than it was able to cover originally. Okay, I'm going to start with an example problem that on the surface has nothing to do with auctions. It comes from the optimal stopping theory. And so what is this example problem? Let's suppose that you're a gambler and you're going to face a sequence of games that you're going to play in. And these games are really dumb games. Each game just draws a value, and you look at the value, and you can either keep that value and go home, or you can give up that value and play the next game. Okay, so we're going to face a sequence of n games. The games have prizes drawn from a known distribution. The gambler knows these distributions, and he has to figure out what he should do each day. Should he keep the prize that he got and go home, or should he give up the prize and go on and play the next day? I went to a Pirates game 2 days ago, and they did this, sort of. This guy on the screen in the back of the Pirates game, he had won some Pirates jersey, and they said, well, you can keep your Pirates jersey, or you can have what's in this box. He went with the box, and it was a little cactus. Okay, so here's the question. How should the gambler play this game? So how would you figure out how to optimally play this game if you wanted the best possible payoff? Okay, well, you could do what's called backwards induction. You think about, okay, let's suppose on the last day I still haven't taken a prize. And I see that prize, what am I going to do? Well, I'm going to take it, right? So what expected value do I get from that? Well, whatever is the expected value of the prizes on the last day. It's the expected value of that distribution. Okay? So on the second to last day, I see a prize. When should I take it? If it's bigger than the expected value on the last day, I should take it. So I'm going to use the expected value of the last day as a threshold for the second to last day. All right, well, let's calculate the expected value I get from that process for the second to last and last day. And on the third from last day, when do I take the prize? If it's bigger than that expected value from the next 2 days. Right? So you could backwards induct and solve for these thresholds, which are going to be increasing as you go backwards, right, or decreasing as you go forwards, of what the best thing to do is if you're the gambler. So let's discuss this optimal strategy. Well, the answer is kind of complicated, right? You get n different numbers back. You have to sort of figure out what these n numbers are. If I said, well, what are some good properties of good strategies? You can't really conclude very much. I guess you could say the prize should, your threshold strategy should decrease over time, right? But other than that, you don't really get much intuition out of what's going on. It's not very robust to small changes in the game. What if we change the distribution above the threshold on the last day? Well, everything changes, right? All the thresholds change, everything changes. It's not very robust, okay? In fact, or you can imagine, reordering some games. Everything changes. Okay, and it's not very general. If I asked you what you learned about sort of variance of the stopping game, if I changed the stopping game in some maybe little way and said what happens then, you wouldn't know. You'd have to solve for that again. Okay, so I want to talk about another approach. So I'm going to call a threshold strategy the following. A threshold strategy is picking one number t, which we'll call the threshold. And what the gambler is going to do is just take the first prize that's over the threshold, and that's it. Okay? And I want to point that this is obviously a suboptimal strategy, right? Because even on the last day, the prize is below the threshold, he just goes home with no prize. It's pretty dumb of him to do that, but we're going to do this obviously suboptimal thing. Okay? And the question I want to ask is, how good can such a gambler do with such a simple strategy? So here's the theorem. If you pick a threshold such that the probability that the gambler on the last day says no and gets no prize, such that probability is exactly 1/2, then the expected prize the gambler gets is at least the expected maximum value that he could have gotten in hindsight if he knew what the values were, over 2. Okay? So why this is called a profit inequality, because somehow the gambler is approximating a profit. Right? You could only get the maximum of the VIs if you knew the future, right? And knew exactly which one to stop with. But the gambler does not know the future, so he can't even do that. Okay? So this says that the gambler does pretty well compared to this hypothetical profit. In fact, he gets a 2 approximation. Okay, let's discuss this solution. It's really simple. It's described by one number t, unlike the optimal solution, which was described by n numbers, 1 for each day. It's conclusive. It tells you really what's going on. You're trading off stopping early with an inferior prize, with never stopping and getting no prize. And you're trading that off with exact probability 1/2. It's really robust. What if I change the order of the prizes? If you change the order of the prizes, does it change what threshold is the right threshold to use? No, the probability that you walk off the end is still the same for every t, so you still pick the same threshold. Right? So the prediction that the suggested strategy does not change as you change the order of the prices. It also doesn't change if you change the distributions above the price or above the threshold or below the threshold. You make those changes, nothing different happens. Okay? And also, the same solution works for similar games. And in fact, when we see the proof of this, we'll see that actually it's invariant to what I'll call the tie-breaking rule. What's the tie-breaking rule here? It's, I picked a threshold as the gambler, right? What if there are multiple prizes above the threshold? The tie-breaking rule tells you which prize the gambler takes. Okay? And in the game, the tie-breaking rule was the one that comes first is the one you take. But maybe there's some other game I want to analyze with a different tie-breaking rule. This proof is actually going to be invariant to the tie-breaking rule, so actually the same result holds for many similar kinds of games. Okay, I'm going to give you this proof in one slide. This is one of the slickest proofs I know. And I can say that because it's not mine. Okay, so let's have some notation. Let's let Qi, we picked a threshold t. Let's let Qi be the probability that the prize I is below the threshold t, meaning the gambler would not take prize I. Okay? And let's let x be the probability that we never stop, meaning all prizes are below the threshold, which is just a product of the Qi's. Okay. I'm going to do something very common for proving approximation results. And what I want to point out, though, is the typical economic approach to optimization tends to use first-order conditions to describe optimal things. Well, to prove approximation results, you tend to prove upper and lower bounds instead. You don't really look at first-order conditions. So it's a very different kind of proof from the standard economic proof. So what I'm going to do is get an upper bound on the expected maximum prize, the value the profit gets. Then I'm going to get a lower bound on the prize that the gambler gets. And then I'm going to plug in x equals 1/2, this choice of t such that with probably 1/2 you get no prize. And we'll see that from the upper and lower bounds, that implies we get a 2 approximation. Okay. What is my upper bound on the expected max? Well, okay, there are two cases, right? Either the max is above t, or the max is below t. If the max is below t, well, we get at least t, right? It's an upper bound. So the max is below t, we get at least t. Good. What if the max, so this term is always bigger than 0, and so we get at least t in the case that the max is below t. And so what if the max is above t? Well, then we get t plus, and this vi minus t plus means just if it's positive. Otherwise it's 0. Okay? So t plus whatever the maximum difference is above t, which is exactly the max. Okay? So this is clearly an upper bound on the maximum prize. Okay, well, expectations of maxes are kind of a pain, but the expected sum is always bigger than that. Right? Good. So that's my upper bound. I'm now going to try to get a lower bound on the prize the gambler gets. Okay. Well, okay. The prize the gambler gets, well, if we never stop, that happens with probability x. So we stop with probability 1 minus x. And we get a prize at least value t. Right? So the gambler gets t times 1 minus x if he gets a prize. But he also gets the value above the prize, right? He doesn't just get t, he gets something more. Okay, so I now want to try to add to this some additional term that takes into account the fact that the gambler actually gets something more when he gets a prize. Okay, but that's going to be a pain to analyze in the case there are many prizes above the threshold. In other words, when there's a tie. So what I'm going to do is I'm only going to analyze this term when there's exactly one prize above the threshold. And if there's more prizes above the threshold, we'll just say we get t. Okay, so if there's one prize above the threshold, then I'm going to add something here. And if there's more than one, I'll just say we get t, which is true. Okay, so I want to add the contribution of every prize conditioned on it being the only prize above t. So what is that? I sum over all prizes, the expected value of that prize exceeding t, conditioned on all other prizes being less than t, times the probability that all other prizes are less than t. Right? And that sums the expected contribution of this prize when it's the only one above t. Okay. What is this term? The probability that all the other prizes are less than t? Well, it's just a product of the qj's not including I, right? And that is bigger than x, because x has an additional qi multiplied by it, and qi is less than 1. So what I'm going to do is factor out this term x and get something that's less than that. Okay? All right. Let's look at this conditional expectation. It's a random variable vi, and it's conditioned on a bunch of other random variables that are independent of that random variable. So I can just drop the conditioning. And now I'm done with my lower bound. And now let's look at these two bounds and notice what happens if we plug in x equals 1/2. If I plug in x equals 1/2 here, I get exactly half of this. Good. Any questions? One of the slickest proofs I know. Okay. So I want to talk a little bit about the philosophy of approximation, because when you apply approximation in an economic settings, you have to be a little bit worried, right? Because let's suppose that we were called in to consult for the widget company that was selling widgets over the internet. And they're like, I need an auction mechanism to sell my widgets. And you're like, oh, okay. Well, I know a great tool approximation to your revenue. So you'll be guaranteed to get half the revenue you could have gotten with something better. And the guy would say, well, screw you, because I want all my revenue. I don't want half my revenue. So that's why we have to remember that we're actually really doing theory with auction theory and not trying to, our goal is not really the exact end result. Okay? And my first point is that approximation helps identify which aspects of the models are details and which are not. And this is something important if you're familiar with what's called the Wilson doctrine, which, so this was a critique of mechanism design that said that, you know, mechanism design would be much more relevant if the mechanism it predicted were less dependent on the details of the environment that they were designed for, right? Because maybe you got the details kind of wrong. Maybe you didn't model the costs exactly as they were. Right? And you would be nervous if that really changed the mechanism design result. Okay? Well, approximation lets you identify which parts of the model are details and which parts are not. And let me give you an example of how that works. Okay, so you might want to know if feature X of the model is a detail. Okay, well, here's the way you can ask that question formally. You say, well, can I get a constant approximation without modeling or taking advantage of X? If so, then maybe it's not the most important thing. Maybe it's a detail. If I can't get a constant approximation without modeling or taking into account X, then it's pretty important. I better model it, and I better figure out how to deal with it. I have two examples of this. My first example is competition. Let's suppose I'm trying to optimize revenue in an auction, and I'm nervous about competition between players being important. Okay? In particular, what if players collude? Then they aren't competing like they should. Right? And what if could that really hurt my revenue? So I'm going to show you the answer to this later, and the answer is going to be no, competition is not that important. In other words, players colluding cannot really hurt your revenue if you design the right mechanism. What about transfers? Let's suppose I'm trying to maximize social welfare. I want to give the object to the player who values it the most, but I can't use transfers. I've got n players. They all kind of want the object. I can't assign transfers. I can't run a second price auction. Basically, the only thing I can do is give the object to a random player, right? And if the players' values are very different, This could be as bad as a 1 over n approximation, right? Because what if n minus 1 of the players really don't care, but they kind of like the object, and one guy really wants it? Then I've just done a really terrible job of allocating my good to society, right? It could be as bad as an n approximation. I think the constant approximation gives very relevant intuition for practice. It helps identify the salient features of the model that are important. And so I can go to that CEO and say, look, if you're worried about competition, don't worry so much. But you should really think about using transfers if you can. It gives simple, more robust solutions. So what I mean by that is, and simple, more robust solutions are actually better to use in practice, because if some of the details of the model are different, then it still actually performs pretty well. And in many scenarios, exact optimization is going to be impossible. And I say that information theoretically, computationally, or analytically. Information theoretically, I mean, this is standard in economics when you say first best versus second best. The first best is impossible, so does the second best approximate first best pretty well? Computationally, because this is a complex mechanism design problem, there may not even be algorithms to compute a solution in a reasonable amount of time. It's intractable. And analytically, a good example of this is the lecture Costas gave, where he said, computationally, we can solve for optimal auctions in quite general settings, multidimensional problems, but analytically, no one's really solved those problems. So no one has come up with analytical solutions to those problems. So it might be nice to analytically come up with approximately optimal solutions to those problems, and we'll do some of that today. I want to show you a picture that I think is especially evocative of really what I think the goal of approximation is. You want to identify what the salient features of an auction are, a good auction are. And so this is a study that Picasso did of a bull, where he tried to distill it to what he thought the essential features of a bull was. And that really, to me, summarizes, I think, the point of approximation. When I want to say what's a good idea, I want to give you a picture that's kind of like this. Questions? Okay, so I'm going to be surveying a number of topics here, very short topics each. To give you examples of how approximation can be used in many areas of mechanism design to get results beyond where exact optimization left off. And as I said, these are going to be really tiny excerpts of chapters of the course notes, which you can look at if you want to see more long examples of these things. Okay, so I'm going to start out in the same scenario where we left off on Wednesday. So we're talking about single-dimensional problems. An agent has a private value for being served, and their utilities are value minus their payment, the standard scenario where Meyerson's theory of optimal auctions applies. Okay, what's the fundamental problem there? It's the single-item auction problem, a single item for sale, a bunch of buyers. The buyers' values are drawn from a distribution, and we want the seller optimal auction. So what is that optimal auction? Well, you guys all know what that optimal auction is, right? Serve the player with a second price with reserve if it's IID and regular. More generally, it's highest positive virtual value, right? Okay, so here's a review of that theory. I want to present that slightly differently from the way I did on Wednesday in the following way. So I want to define a revenue curve for the player to be the revenue I get as a function of the probability I serve them. If I have a player, I'm going to serve them with some probability Q. What revenue do I get? Well, what price should I offer this player to serve them with probability Q? Well, given the distribution, if I offer them the price F inverse of 1 minus Q, then they buy that. That's exactly the price where they buy with probability Q. Okay, so my revenue, if I want to serve them with probability Q, is just Q times F inverse of 1 minus Q. Okay? In general, that'll be some function of Q. Q goes from 0 to 1. Okay? And it turns out that the virtual value that we solved for formulaically on Wednesday is just equal to marginal revenue, meaning the derivative of this function. Okay, so intuitively, this should make more sense than the formula. Right? Intuitively, we look at a player as, let's plot revenue as a function of the probability I sell. Then, as that probability, what's the derivative of that revenue? Like if I sell a derivative more units to them, how much does my revenue go up or go down? That's the virtual value of the player. Okay? Expected revenue is expected virtual surplus by revenue equivalence. And we define regularity to be the virtual value being monotone. And that's the same as this revenue curve being concave, right? Because the virtual value is the derivative of the revenue curve. And so monotonicity of a derivative corresponds to concavity of the original function. Right? So regular means these are nice concave functions. Everybody good with that? And so these are the two main theorems. Sell the bidder with the highest positive virtual value is the optimal auction. But for IID regular distributions, it's actually simpler. It's the second price auction with reserve price inverse virtual value of 0. And that corresponds to the maximum of this curve. Okay? Everybody good? Good, so optimal auctions for IID regular distributions is the Vickery with monopoly reserve price, the inverse virtual value of 0. In the general case, it sells the bidder with the highest positive virtual value. As we saw with this example, that is sometimes some wacky looking mechanism that you really don't see people running very often. You should be a little bit nervous that the IID regular case seems kind of special, and that this auction is actually not optimal in more general settings like irregular distributions or non-identical distributions. So I want to ask the question that I sort of alluded to on Wednesday, which is, well, when is reserve pricing a good approximation to the optimal auction? When can just using reserve prices be pretty good? And so here's the theorem I want to present. And that is, well, if I use the second price auction with reserve, and I set that reserve price to be a constant virtual price. Okay, what does this mean? So I'm going to look at the virtual values of the players. I'm going to get a set of reserve price that's the same virtual value in virtual value space. Okay, but it's going to have different actual price in value space. And if I set that constant virtual price such that the probability that no one wants to buy the object because the reserve prices are all too high is exactly 1/2, then my revenue is a 2 approximation. Does this theorem look at all familiar? Here's the proof. Apply profit inequalities with the tie-breaking rule of by value. Okay? So we're going to apply profit inequalities to the virtual values of the players. Okay? So what does that mean? That means I want to use a threshold in virtual value space. And the profit inequality setting would say, take the first guy whose virtual value is above the threshold, the virtual threshold. Right? But this is not what the second price auction does with the reserve. Who wins in the second price auction with the reserve? The player with the highest value above the reserve price. So when there are multiple people above the reserve price in this auction, the player with the highest value wins. So it's just the same thing, but tie breaking by value instead of by the first one who comes first. Okay? So here's the more details of this proof. So the profit inequality, we had prizes, we had a threshold, we had a maximum prize, we had the prize from the profit. And we just make a mapping from prizes to virtual values, the threshold to this uniform, this constant virtual price. And then the expected maximum prize is the expected maximum virtual value. Okay, so that's the optimal revenue. Right? And then the Vickery revenue with reserve is the revenue that we get by the 2 approximation bound. Okay? Yes?
Just to be clear, if we're running this, we have a constant virtual price for everyone, but if they have different distributions, then that means each one has their own reserve, right?
That's correct. That's a very good point. So let's discuss this. Constant virtual price, bidder specific reserves. Okay? It's much simpler auction, though, than the optimal auction, which has to, invert these virtual value functions to figure out exactly what it's doing. And the virtual value functions matter everywhere. Okay, so it's a much simpler approach than the optimal auction. And it's robust. Why do I say it's robust? Well, the fact that I did the second price auction over these reserve prices didn't really matter, right? In fact, you could just post these prices, and the first guy who showed up could take that wants to buy at these prices could take the object, right? So in fact, collusion isn't even an issue, right? So this is actually robust to collusion too.
So I'm confused. Aren't we setting different prices for different people?
We are setting different prices for different people. So the first person who shows up and wants to accept their personal price, I'm happy to serve the object to.
So are there examples of this kind of mechanism with personalized pricing?
Personalized reserve prices? Yeah, look at sponsored search on the internet. So if you are selling advertisements, these advertisers get different reserve prices based on all kinds of things, like their quality score and all kinds of stuff. So these actually do arise. But I want to address the real complaint here. Is really you guys are like, well, this using different reserve prices is kind of unnatural too, right? And the hope was to get something more natural that actually is used a lot more often in real life. And so here's the question you guys are asking, which is what about non-identical distributions and an anonymous reserve price, the same reserve price for everybody? Is that good? And so, and the example I like of this is eBay, right? So eBay uses an anonymous reserve price. But do you think that the bidders in eBay are identically distributed? Well, note that eBay keeps a lot of information about individual bidders, like a reputation. And so different bidders have different number of stars by their name, which is their reputation. And maybe a bidder that's got a high reputation is more likely to pay a seller, right? So maybe sellers want to somehow prefer these bidders and not run a symmetric reserve price, right? So here's the theorem. For non-identical but regular distributions, the second price auction with anonymous reserve price is a 4 approximation to the optimal auction. Okay? You can prove this using a more complicated extension of profit inequalities, which I'm not going to go into. We've already seen a couple of proofs by that technique. You may wonder if that 4 approximation is tight, so this is kind of a worst case bound. It says come up with some crazy distributions that are non-identical, and then what's the worst we can make the anonymous reserve revenue from the optimal revenue. So that 4 is not known to be tight. The actual bound is somewhere between 2 and 4, and this is a great math question to try to answer, is what is the actual approximation bound of an anonymous reserve price versus the optimal auction in a non-identical but regular environment. Okay, I want to talk very briefly about some extensions of this model. So we were talking just about single item auctions, and you can extend these techniques to more general kinds of auction environments with single dimensional preferences. And in general, you can come up with posted pricing mechanisms that are often going to be constant approximations to the optimal mechanism. Here are 2 references to papers that do that. How do you tend to prove these kind of results? Well, in single dimensional settings, we know the optimal mechanism is just the virtual surplus maximizer, thanks to Meyerson's theorem. And then we just have to show that reserve pricing based mechanisms are virtual surplus approximators, that we can somehow get a bound, an upper and lower bound to show that the approximation mechanism is doing well. So that's how you tend to analyze these kinds of approaches. So the basic question we were asking here is, when do simple natural auctions approximate the more complex optimal auctions? There are some main challenges in doing so. So one main challenge right now, an open question, is coming up with good simple mechanisms when you have a non-downward closed environment. So what I mean by downward closed environment, a downward closed environment is one where if I'm serving multiple agents, then I can serve a subset of those agents, and that's still feasible. Okay? So what's an example of a non-downward closed environment? The public project example we talked about before, right? You serve everybody or nobody. I'm serving everybody. I'm not allowed to just drop some of the agents and serve a subset of those. That's not allowed by the set system. Okay? So coming up with good approximation mechanisms for public good type problems is an open question and a good problem to study. Questions? Okay, so the next topic I want to go into is multidimensional mechanism design. So here the goal is to optimize revenue again. We have distributions, but the players have multidimensional preferences. And so the simplest example you can think of is there are multiple objects for sale, and you have a different value for each of the objects for sale. Okay, so that's the exact setting I'm going to start with. Let's just make it easy. Instead of doing an auction, we just have one consumer. Okay, there's one player, one consumer, and a bunch of houses that he might want to buy. He only wants to buy one of these houses. He has a distribution, a product distribution for which his value for each of the house, right? And we would like to post prices on the houses such that when the consumer realizes his values, and then takes the house that maximizes his value minus price, then we as the seller maximize our revenue. Okay, that's a multidimensional screening problem. If you're an economist. And so the question is, what is the optimal pricing? Everybody clear? Good. So here's one solution to that. You consider the distribution, the feasibility constraints, the incentive compatibility constraints. You write these down in a big program. You push the solve button on the program, and out comes, hopefully, some answer. That is, unfortunately, the only solution, general solution people have. And I argue it yields very little conceptual insight to what good solutions look like. And also, this problem is not generally tractable. Okay, so we don't expect there exists this magical solver that will actually output good prices. Okay? Okay, so I would like to come up with an approximation to this problem. I don't know what the best prices are. I would like to come up with prices that approximate the best prices to guarantee something good, and I'd like to get some intuitive understanding for what makes those prices good. Okay? So, and here's the challenge I face, right? I'm trying to approximate something, and unlike in the single-dimensional setting, in the single-dimensional setting, I know what optimal is maximize virtual surplus, right? But now we're trying to approximate something that is the outcome of some complicated program I don't understand. So how am I going to approximate that? So here's the idea. I'm going to try to find an upper bound on that optimal revenue from a pricing that I do understand. And to do that, let's compare two problems. So here I have the pricing problem we were just talking about. Single consumer, unit demand, they want to buy one of these houses, value from a distribution. Here is another problem that we've talked about a lot already. A single item for sale, a bunch of buyers, a distribution, and we want a seller optimal auction. Right? We know the answer to this. We don't know the answer to this. But like the syntax of these problems is the same. Right? You pick one thing to serve, right? And the same distribution, it's a product distribution. So maybe we can compare these two. So here's the point. Let's suppose you were a seller and you had a choice of a situation. Which situation would you want to be in? This situation or this situation? Which seller would you rather be?
Doesn't matter.
Huh?
Doesn't matter.
It doesn't matter?
I don't.
Any alternative opinions? You'd rather be the auctioneer, right? Why? They're competing with it. They're going to compete with each other to drive the price up. Whereas on the left, they're not competing. Right? So you post prices, they're going to get whatever maximizes their utility. Here you post prices, they still might actually bid, like if you ran an auction, you posted prices, they would bid above it, right? So you'd be happier being this seller. Okay? So that's a theorem actually. The optimal auction has higher revenue than the optimal pricing. Good. So I have an upper bound, right? That I do understand. I understand what's going on here. So now my goal is to come up with a pricing for this problem that approximates that. Any ideas? Okay. And in particular, use the posted pricing we already came up with that was good. Right? So a constant virtual price with probably 2 being accepted by the buyer is going to be a 2 approximation. Why is this? Profit inequality, tie breaking by minus PI. In other words, you know, what's the worst that could happen if you post prices and he has multiple values above the price? He takes the one with the smallest price. Right? That's the worst that could happen. Okay, so tie break by minus PI in the profit inequality, and it shows it's a 2 approximation. Great. And one of the things I really like about this theorem is that, you know, it's a very, like, it's, when I said, like, what's the optimal single item auction? And you say, serve the player with the highest positive virtual value, right? Like, if we know the language, we know what virtual values mean, you can tell me in a sentence what that is, right? If I said, what's the optimal posted pricing, you're like, well, put it solver, right? I don't have a nice description. But here I do, right? It is a uniform virtual pricing where the buyer has a probability 2 of accepting. Single sentence, tells you what it is. You get some great intuition for what's going on, hopefully. Okay, so that was just one player, but we can add more players. Let's call a sequential posted pricing the following. The agents show up one at a time. We offer each agent pricing over all the objects. They take whatever they want, and then we continue with the remaining supply. And you can show that in many unit demand settings, sequential posted pricings are a constant approximation to the optimal mechanism, meaning if you're running a grocery store, just put prices on your items and you'll actually do pretty darn well compared to the best auction had everyone shown up at once, submitted their bids, and you optimized with this program that doesn't exist because it's computationally intractable.
What does sequential posted pricing mean?
Yeah, so it just means I'll let the agents arrive one at a time, and each one will get a take it or leave it offer of any of the options they want, and they'll do whatever they want. And then some of the objects will be gone, and then another agent will arrive. Okay? And in fact, the prices that come out of this, sometimes the agents can come in any arbitrary order. You don't even care what order they come in. And the prices don't change as you sell stuff. You just keep the same prices over all time. So the grocery store posts the prices. People come in whenever they want. They buy stuff, or they don't, and they leave. Yeah, so for instance, if I had n players and n houses and I did this, the bound would be 6.25. That is not known to be tight, so improving that maybe is interesting. I want to give you a quick overview of how this kind of proof proceeds. And it's going to be basically the same as what we did before. The question?
Yeah. So in this case, in order to compute that, the grocery store would just have to know enough about the distribution to know, like, ex ante, what will lead to 50% for the whole customer population? Or what do they have to know to implement your approximate solution?
So let me answer that question in a second. Okay? That's a good question. I'll answer it when I'm done with this. So here's the approach to showing a bound like this. Okay? I'm first going to define an analogous situation which is single dimensional. What I'm going to do is replace each multidimensional unit demand agent with a bunch of representatives that each want each of the objects. And I will assume that those representatives don't talk to each other and they compete with each other. Okay? And then my claim is that this single dimensional auction problem gets more revenue than any multidimensional pricing solution. Why is that? because the agents are competing with each other. Okay? Then I'm going to try to give a reduction. I'm going to try to show that multidimensional pricing gets me more revenue than single-dimensional pricing. If I'm just going to post prices on items and these representatives show up, well then there's no competition being exploited by this pricing. Okay? So it doesn't actually matter if the person was a single-dimensional representative or a multidimensional single person. So I'll show that the multidimensional pricing actually gets more revenue than single-dimensional pricing. And the reason why it's bigger is because in a single-dimensional pricing, these representatives may come in some weird order, whereas in the multidimensional case, you show up all the time with all of your demand. You don't show up in different orders. So, and then you have to instantiate this reduction by showing there exists a single-dimensional pricing that's a beta approximation to the single-dimensional auction problem. And then you can put together all these inequalities to realize that the multidimensional pricing is a beta approximation to the single-dimensional auction, which is an upper bound on the best pricing. And so you got to end up a beta approximation. And this is actually exactly what we just did with our 2 approximation for the single player. Let me now answer your question of how would you come up with reasonable prices? And you do this. You figure out what reasonable prices are for the single-dimensional problem. And the way you do that is by looking at what the optimal thing does and trying to simulate what it's doing. And you know what the optimal thing is doing because it's a single-dimensional problem. It's just maximizing virtual surplus. Okay, and that's something that we have a good understanding of, and we can figure out what it's doing. And then we'll post prices that simulate what that's doing. Okay, simulating the competition that happens in that environment.
But I still start with the distribution of various values.
Yes. Okay, so I want to discuss this theorem a little bit. It's robust to agent orderings, collusion, etc., versus the optimal auction, which was not robust to these things. It tells you that some conclusions about auctions, which are competition is not that important for approximation. You can actually get very good approximations without taking into account the fact that the players are competing with each other. And it tells you something about, so throughout this assumption, I was assuming these players were unit demand. They want one of these houses. It says that unit demand incentives are kind of like a bunch of players with single-dimensional incentives. Okay, so they behave very similarly. It also is practical. Posted prices are widely prevalent. In fact, eBay is switching from auctions to buy it now pricing because they're good approximations and actually they have lower costs for the players. Okay, so it's a really good move for them. Okay, I have a couple open questions in this area that I think are really great questions for future research. And that is, the first step in showing that you have a good approximation was coming up with an upper bound, a good upper bound that we understand. And this upper bound of the single-dimensional representative environment where I replace each consumer with a bunch of independent consumers, that upper bound requires this unit demand assumption on the players. For instance, if a player was additive, their value was the sum of the values of the houses they bought, then this upper bound wouldn't work. Okay? So it's known to be wrong. It's false that this is an upper bound. So the biggest question here is coming up with upper bounds for non-unit demand settings, more interesting settings that are analytically tractable, and you furthermore get a good approximation to them. Yeah?
So the statement, you can relax the sequential posting assumption and you would still have a constant approximation, right? Because the MD, you showed that the multi-demand pricing.
What do you mean relax the sequence?
Assume that people aren't coming in one by one, they all just sort of.
They show up and I run like the Vickery auction with these posted prices instead. Yeah. Yes, so that's a good point. If I have posted prices that are good, then running the Vickery auction, the VCG mechanism with those posted prices as reserves always just improves my revenue. So that would be a good, if you're actually designing a mechanism, you would do that instead of the posted prices. Questions? More questions? Yeah.
You know, references of approximations of mechanisms where you're looking for insurance, for example, with prepaid concave utilities?
That's a great question. So the question is, there are two big challenges in mechanism design. And one is multidimensional preferences, and the other is nonlinear preferences. So in the single dimensional problem, we had preferences which were value minus payment, linear function. The utility was the linear function. In the unit demand case, we also had value minus payment being the utility, so it's still a linear function. So the other big challenge in mechanism design is nonlinear preferences, like risk aversion and such. I do have a reference for you, and there is a new approach that's based on the fact that the optimal auction in single dimensional settings was like looking at this revenue curve and the derivative of that, and then optimizing, giving the player with the highest derivative of the revenue curve. You can ask the exact same question even if players have nonlinear preferences. Like they have some curve, you say, what's the revenue curve that I get from this player? And then you can optimize marginal revenue, and you can prove this is a constant approximation. So I'll give you a reference to that after the lecture. Okay, I want to move on. One of the things that you'll notice in the last two sections, getting approximation mechanisms, these approximation mechanisms were much less dependent on the distributional assumption, right? I didn't use the entire distribution to come up with this anonymous reserve price that I posted to get a floor approximation for a single item auction. I just needed to know one number. I don't need to know all these virtual value functions, right? So these auctions you get are less dependent on the distributional assumption because they're much simpler. I now want to take that question to the extreme and ask, well, can I design auctions that are good without any distributional assumption? Meaning, suppose I know nothing. I want to sell an item in an auction and I don't know anything about the players. What can I do? Okay, so I want to point out some issues with the prior assumption that we were making all of Wednesday and most of today. Okay, so the prior assumption was we assume the players have values drawn from a distribution, and to come up with the optimal auction, we optimize our revenue and expectation over this prior distribution. So we do like an average case analysis for the given distribution, which we had to know to do the design. Where did we get that prior from? Okay, two places you could have gotten the prior from. You could have gotten it from previous experience you had in the market, or you could have gotten it from market analysis. There are two problems, one with each of these places you have the prior from. Let's suppose you're repeatedly interacting with players, and you use their past interactions with you to change what you do in the future against them, right? Well, that's going to affect the strategic incentives of their past interaction with you. So you got to be very careful about that. Okay, so I'd be nervous about getting the prior from previous interaction with the same players. Okay, what about market analysis? Well, if I do market analysis, I better not be doing market analysis on the same people who are going to show up in my market for the same reason, right? And so I have to have some market analysis elsewhere. And I'm going to be nervous if I'm assuming in my analysis that my market is very big, whereas for market analysis, but my auction problem has a very small number of players. Right? And auctions are really only interesting for a small number of players. If there are lots of players, then just post prices. Who cares about an auction? Okay, so if we're in a small market, it's really kind of weird to assume that we had a continuous distribution that we knew exactly. Right? What if I'm selling supercomputers? There are 5 organizations in the world that want to buy a supercomputer. How am I going to get a continuous distribution that models these players' preferences? I've got at most 5 data points. But if I get those 5 data points, then I can't run the auction on them because they would manipulate their data points, right? Is the prior accurate? It doesn't take into account possible errors in the prior assumption. Usually when you do distributional analysis, you get errors, and how does that take into account in designing the auction? We didn't even take that into account at all. Prior dependent mechanisms are not very robust. If the prior is not what I thought it was, then my revenue is affected. And the last thing, which I think is really one of the most important things, is what if I need to come up with one mechanism that's going to be used all over the place in more settings than I've analyzed, right? So I have some examples of this I really like. So as a computer scientist, we design internet protocols, and for instance, the protocol that routes packets back and forth in computer networks is a protocol that gets used with strategic agents who all want their packets to get there as fast as possible. right? And you don't get to design a new packet routing protocol for every different application that wants to use the internet, right? Basically, TCP/IP does almost all the routing of internet traffic, and it's the same protocol everywhere, right? And the remarkable success of TCP/IP is that it's one protocol that was actually pretty good for almost all workloads. Sure, it's not the best for some workloads, but it's basically pretty good, and so no one changes it. Okay, so I'd like to try to design good auctions without any knowledge of the prior distribution. So what's an optimal prior independent mechanism? Well, you could run the following mechanism, right? So the players actually maybe do know the prior because they're in Bayes-Nash equilibrium, so they have to know the prior, right? So what I do is ask agents to report their value and the prior. If they disagree on the prior, well, that can't happen because we have a common prior model, so we shoot them. And then we just run the optimal mechanism for the reported prior. We're done, right? So I have a number of complaints with this mechanism. The first thing is I just ask agents who had a single value for the object I was selling to report a hugely complicated object, the prior, right? That's just kind of like wrong. Why did I ask agents to report this ridiculously complex thing when they only have a single private value, right? It's really not robust. If agents make mistakes, I shoot them. We get no revenue. And I say, well, it doesn't really conclude anything about this question I wanted to ask of how do I design mechanisms without prior information, because it begs that question. It just, you know? Yeah.
It's not strategy proof, is it?
It is.
So we could all get together and report up to the same prior, which is incorrect?
That's collusion, which is different from strategy proofness.
Oh, okay. Yeah.
Right?
So there are bad equilibria.
There are bad equilibria. And so actually there's a field called implementation theory that tries to get rid of the bad equilibria in this mechanism by getting slight variance on this mechanism that don't have the bad equilibria. But I don't think slight variants of this mechanism are very interesting either for all of these reasons. Okay, so I'm going to give you a couple approaches. My first approach is going to be resource augmentation. And I put that in quotes because I don't really mean resources. So what do I mean? The theorem is known as the Bulow-Klemperer theorem. It says for IID regular single item auctions, the second price auction on n+1 agents has higher revenue than the optimal auction on n agents. In other words, if I am allowed to do some advertising for my auction and get one more player to show up, I get more revenue than if I did market analysis and figured out what a good reserve price was. Okay? And I argue that recruit one more bidder is kind of a prior independent strategy. I didn't need to know what the distribution was that the bidder's values were drawn. I just had to put a billboard up. And it's also what is often called a by-criteria result. It says that if I give the approximation mechanism a little bit more power, a little bit more resources, one more player, then I can do as well as an optimal mechanism that has fewer resources. And resources, again, is one more was the agent that showed up. Okay? And it has a nice conclusion, which is that, you know, sometimes competition is maybe more important than optimization, right? Having this competition between the players that drives the price up is more important than actually optimizing what a good reserve price was. One problem, though, is that this result, it does generalize, but not as nicely as you'd like. Right, let's suppose you had k identical items, and you wanted to generalize this result to say, well, if I just did a second price auction or a k plus first price auction, right, when will I get the same revenue as the optimal auction? Well, you'd have to add k more bidders, right? And this starts to get ridiculous if I'm thinking maybe, well, what if I have a digital good, meaning I have n players and n items? It says in order to get at least the revenue, you have to double your market. Well, maybe doubling my market is not such an easy thing to do. Okay, so what should I do instead? Okay, I want to, before I get to that, I want to actually prove a special case of this theorem. So the special case of this theorem is the n equals 1 case. Okay, so what does this theorem say in the n equals 1 case? it says the second price auction with 2 players has more revenue than just posting the best price for 1 player. Right? Because the optimal auction for 1 player is just to post a price to them, right? I want to give a geometric proof of this, which is due to Tim Refgard and his students. And here's the proof. So from each player's perspective in the second price auction, the other player's value is just like a random reserve price, right? Great. So Vickery's revenue is twice the revenue that I would get if I had a single player and offered them a random reserve price from the distribution. Right? Because I have 2 players, and they both feel like they're getting a random reserve price from the distribution. Okay, so the last thing I need to show then is that a random reserve price is at least a half of the optimal reserve price. Because then twice the random reserve price is at least the optimal reserve revenue, which is the statement of the theorem. Okay, well, how do you show that? Well, remember our intuitive pictures of auctions where we had this revenue curve, which was the probability times the price that gets accepted with that probability, which was this revenue curve? Okay, we're assuming regularity, which means this revenue curve is concave. Okay, so what's the optimal revenue? Well, the optimal revenue posts price Q and gets revenue R Q star and gets revenue R of Q star, which is that. But that's the same as this rectangle, which is 1 times R of Q star. Right? So geometrically, that's this rectangle. Well, if I offer you a random reserve price from the distribution, well, that's just like drawing a random Q from uniform 0, 1. Okay? And if I take what's your expected revenue from any particular Q, well, I read it off this axis. It's that point for this Q here. Right? So for a random Q, it's just the integral of this area is your revenue from a random reserve price from the distribution. And now I'm showing the random reserve is at least half the optimal reserve, and that's by the fact that the rectangle is no more than half the triangle, and this was a concave function, so the triangle is smaller than it. Everybody good? So the second price auction with 2 players is at least the optimal revenue of 1 player. What's really great about this approach to the Bülow-Klemperer theorem is that it tells you something really interesting about reserve prices, right? It says that maybe there's a sense in which a random price from the distribution is almost as good as the optimal price, the optimal reserve price, the monopoly price, the thing that optimizes this revenue. And that's exactly true. So let's suppose we want to maximize revenue and we have a digital good, meaning we have n copies of an item and n players. Here's the technique for, well, the optimal auction does what? Well, it just posts the inverse virtual value of 0, right? If I have n players and items, maximize virtual surplus, which means sell to anyone who's got positive virtual value, which means post the price inverse virtual value of 0. Okay, optimal simple, not prior independent. So if I wanted a prior independent version, here's how I could do it. Okay, and this is what's called the single sample mechanism. Pick a random agent as a sample, offer all other agents the value of that agent as a reserve price, and then reject this player. The poor guy doesn't win. You could also just give him the item for free. It doesn't really matter. Doesn't change your revenue, doesn't change his incentives. And then the theorem is, for IID regular distributions, this single sample on n plus 1 agents is a 2 approximation to the optimal auction on n agents. Right? And that's now kind of obvious, right? Because each one of these players is like, well, do you give them the monopoly price, or do you give them a random price from the reserve? And from the previous theorem, we saw that a random price from the distribution was half the revenue of the monopoly price. The inverse virtual value of 0. Okay, some conclusions. It's prior independent. It's conclusive. You can learn the distribution from the player's reports in the mechanism. You don't have to have them cross-report. So let's compare this with the optimal mechanism before. The one we didn't like, where we said agents report their value and the distribution. These agents are cross-reporting on what other agents' distributions are like. Okay, so instead of doing this cross-reporting, I can actually learn the distribution on the fly as I'm running the mechanism from the reports of all the players. So players just report their values, and from that I learn the distribution.
How do you generate incentives for player I to report these true values?
Well, first off, the players don't know if they're player I.
Okay.
So I pick that, first they bid, right? Then I pick a random agent. And so if he's player I, he doesn't care what happens, right? If he's not player I, he gets offered a reserve price, and the only way to always win at the right time is to say his value. Right? It's the same incentives as the Vickery auction.
Okay, all right. Thanks.
Okay? So, and here's one of the conclusions that I really like, actually. So one of the problems with the economic theory of optimal auctions is it assumes a continuous distribution. When we did like market analysis on an infinitely big market, right? That's ridiculous. How small can we make the market before we can't get good auctions? 1 is enough to get good auctions. 1 sample. That's pretty amazing. Of course, more samples improve your approximation ratio. Okay, but 1 gets you half the way there, which is, I think, a really amazing result. Okay, there are some extensions to this. Non-identical distributions. This was assuming IID with a single sample result. You can do non-identical distributions also. You can also, this was for single item or digital good problems. You can also do various constrained auction problems where you have feasibility. These are, again, downward closed. So there's some set of agents you can serve, some you can't, and any subset of a feasible set you can still serve. Yeah? Yes, you should worry about collusion, but in the regular Meyerson auction, you have to worry about conclusion too, so it's not really a fair comparison. Right? But you definitely have to worry about collusion in auctions in general, unless you're doing the posted pricing mechanisms I recommended in the first part of the talk. Yeah, and so you can also extend this to multidimensional preference problems like multi-item auctions. There's some papers that do that. So I think the biggest open question here is non-downward closed environments. Again, these are the big challenge for approximation. Questions? Yeah.
Yeah, so the earlier mechanism that you pointed out where you have people report their distributions and choose them if they disagree, I mean, there's something sort of along those lines, but that doesn't require too much complexity, which is like you auction off the right to become the auctioneer, right? So do you know anything about, granted, like that has a problem that you're still assuming that the agents know something about each other's distributions in the analysis, but if that's true, do you know anything about how good an approximation that would do?
So those approaches don't tend to be as good as the Bulow-Klemperer theorem gets you. And here's why. Just having one more player, if I just had one item, just having one more player is better than doing the optimal auction for n-1 players. If I sold the rights to some player, then he's doing an n-1 player auction on the other players, and that's probably not going to be as good.
But it seems like what you're doing here, where you draw one sample and then discard that player.
Yeah, so if there are many items to sell, then this approach will do similar kinds of things to this, doing something like that. So yes, you can do those kind of approaches are reasonable. I like the mechanisms that don't require cross-reporting at all. For instance, this single sample mechanism is actually dominant strategy instead of compatible, whereas that mechanism is not. Like the agents have to know the prior distribution to be able to run that mechanism. So this actually gets the same result with a much stronger solution concept. Any more questions? Yes?
So for the result to hold the IID assumption, you got a strong assumption.
So as I said, there's extensions to non-identical distributions. But the result I gave you with a single sample does require IID. The way to extend this result to non-IID distributions is the following. Notice that if I was doing the optimal auction with non-identical distributions, then the optimal auction discriminates between the players. Right? So how would you come up with a good setting to explore prior free auctions that was similar? Well, what if I had the players clustered into groups based on their distribution, right? And here's a way to ask the prior independent question. What if I don't know the distribution of each group, but I know which players are in the same group? Okay, then I would like to come up with a mechanism that approximates the optimal mechanism that does know the distribution of each group, but just that it doesn't know the distribution of each group. So here it allows non-identical distributions amongst players in different groups, but in the same group they have the same distribution. As long as each group has at least 2 players in it, you can do the single sample approach using 1 player from each group as a sample.
Whenever you start sizing, like the people have like common value, so their valuation of the item is the same, but they each receive the same amount. And in this situation, so say for the second order, second price auction, the result will be quite different.
So absolutely everything I've been talking about today and Wednesday has been for the private value model and not a common value model. And I agree completely that looking at approximation and common value models is a fantastic question. That there's essentially been no work in that. So it'd be a great thing to explore. So I don't have any answers to that kind of a question. But it's a great question, and someone should do that study. Yeah?
So I'm wondering if there are any results on maybe approximation where we don't look at the worst case, but maybe think a little more about how it would perform in practice or on average. Is there any way to approach that, or do you think it's a good question?
So the question I think is good here is how to take advantages of parameterized assumptions on the distribution. Like log concavity and like what is the, like gives you a parameterized class, and you can then maybe say for the various parameters auctions perform better. One way, so you have to be careful about what's a good theory question to answer. For instance, if you gave me any particular distributions, I could just simulate the thing and see what the approximation factor was, right? And actually doing the math for particular distributions seems like a waste of my time, right? So you'd have to have some kind of parameterized class and trying to show better approximations with parameterized classes. The approach that people have taken to this in the literature so far has been looking at really coarse parameterization. So looking at monotone hazard rate distributions, or looking at regular distributions, or looking at all distributions. And there hasn't been kind of a, let's parameterize based on, you know, how, whatever extreme the distributions are. You know, really for the asymmetric results, you'd want to parameterize based on how asymmetric the situation is. And I don't have a good answer to how to do that. But doing that well would be, I think, very interesting. Any more questions? Yeah.
So at a fruit stand in another country where I might barter for the item versus a fruit stand around the corner where I pay a fixed price, I mean, does that tell me something about the distribution that they expect the customers to have? Or
does the price they offer tell you something about the distribution?
No, I mean that one situation you have a fixed price setting, in another situation, they're going to barter with you, which is.
So I don't know much about the bartering literature. My expectation is it's probably more social custom than really driven by like the game theory of the setting is such that you would want to do this. But I don't know. I think it's a good question.
There's also the view that like you're trading off the time cost that you spend bargaining against the volume of goods, right? So people you buyers are more heterogeneous in their cost of time in their setting.
I think one aspect of it is that a seller has an advantage in being able to commit. Whoever has commitment power has advantage in negotiation, and the sellers here have decided to take that advantage. And the sellers in other countries where they allow you to barter, I guess, at least haven't told you that they're taking that advantage, right? So I'm going to skip the section on computation and just conclude. And my conclusions are basically that approximation can help tell you like what's are important properties of good mechanisms. In fact, we learned that reserve pricing and posted prices were good ways to approach mechanisms. We learned that you can design good mechanisms without prior information, and in fact that one sample from the distribution is often enough to design a pretty good mechanism. And we didn't learn this, but we could have if we had more time.
Thanks for the awesome talks.